So in this video, we're going to be talking about atoms, molecules, and subatomic particles. So the idea of the atom extends back at least 3,000 years, and in modern chemistry, we adopt a view of matter that is called atomistic. What that means is that we consider matter to be built of fundamental blocks that we refer to as atoms. And so all of the different forms of matter that we see around us are built up of these building blocks called atoms. The atoms come in different types and styles, and we assemble them in different patterns in order to create all of the samples of matter that we see around us. So this is kind of an idea that dates back to the ancient Greeks, in particular a guy called Democritus, who lived around about 3,500 years ago. So in modern atomic theory, we describe matter as being composed of particles called atoms, and these particles are indivisible by either physical or chemical methods. So the modern atomic theory was first expressed by a guy called John Dalton in the beginning of the 19th century, and he came up with 5 postulates. He said that all matter is composed of tiny indivisible particles called atoms. So this is in common with what Democritus and earlier people had said. He then said that atoms of a given type are the same as each other, but atoms of different types are different from each other. So what that really means is that every carbon atom is the same as every other carbon atom, every hydrogen atom is the same as every other hydrogen atom, and so on. But carbon atoms are fundamentally different from hydrogen atoms. His third postulate was that the number and arrangement of atom types in a pure substance determines its identity. So atoms are our building blocks, and how those atoms are, or those blocks are connected to one another, the number of each type of block, that's what determines the physical and chemical properties of a substance. His fourth postulate was that when a chemical change occurs, the atoms become separated, rearranged, or combined in different ways. So what we're doing when a chemical change or a chemical reaction occurs is we're making new connections between atoms, we're maybe perhaps breaking some old connections between atoms, or we're reorganizing the pattern in which the atoms are connected. And Dalton, very importantly, in his fifth postulate states that in a chemical reaction or a chemical change, atoms can't be created, they can't be destroyed, and they can't be transformed into other kinds of other kinds of atoms. So really this kind of reinforces the idea expressed in postulate number 4 that when a chemical reaction occurs, all we're doing is we're just scrambling up the way that the atoms are connected to one another. We're not making any new atoms, we're not destroying any atoms, and we're not turning one kind of atom into another kind of atom. So how big is an atom? An atom's about 10 to the minus 10 meters across, and it weighs around about 10 to the minus 23 grams. So atoms are tiny. Perhaps the most well-known way of visualizing atoms is with this tool called a scanning tunneling microscope. And what's happening here is a tip that has one atom at its tip is dragged across the surface, and it literally detects these atom-sized speed bumps as it goes across, and we can create an image of the surface. So this is an image of a silicon surface here. And this is an image that was created. If we lower this tip down, we can actually pick up atoms off the surface and we can stack them up. And this is an image of xenon atoms spelling out the letters IBM that was created in this way. Okay, so modern chemistry adopts an atomistic view of matter and says that matter is composed of indivisible building blocks called atoms. When different types of atoms combine in characteristic ratios and in characteristic patterns, we form compounds, And an important idea is that atoms of a given type cannot be divided or transformed into other kinds of atoms. So atoms may combine by forming chemical bonds to form what is referred to as a molecule. So a molecule is two or more atoms chemically bound together, and molecules can be classified on the basis of the number of atoms that are in the molecule. So for example, a molecule containing two atoms is called a diatomic molecule. A molecule containing three atoms is called a triatomic molecule. Generally, when we go beyond three atoms, we'll refer to our molecule as being polyatomic, and poly just means several, so several atoms. The atoms in a molecule are bound to one another via a chemical bond, which we'll learn about later, and it is not possible to break a chemical bond by a physical process. For this reason, molecules are often described as being the limit of physical subdivision. Another way of thinking of a molecule is as a single discrete package of atoms. These atoms are stuck together and they can't be broken apart other than through a chemical change. There are 7 elements that appear in nature as diatomic molecules, and these are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. You can remember these because they are hydrogen, and then if we hop on over to number 7 and draw a 7, we get the remaining 6 elements. So H2 over here, there we go, and then we hop on over to number 7 and we draw a 7, and that gets us the remaining 6. Another way of classifying molecules is as either being homoatomic or being heteroatomic. Homoatomic means that your molecule contains only one type of atom. If your molecule is homoatomic, then it's going to be an element. Heteroatomic means that your molecule contains more than one kind of atom. If your molecule is heteroatomic, then it's going to be a compound. It must be a compound. Now, there is another class of compounds that we're going to talk about later on that are not at all made of molecules. These guys are made of electrically charged particles called ions. And so these guys are referred to as ionic compounds. And in ionic compounds, there are no molecules. Rather, the compound exists as an approximately infinite repeating pattern of these positive and negatively charged particles. So there's no discrete molecule, there's just this extended three-dimensional network. So that makes it kind of hard to define what is the formula of one of these compounds. And what we do there is we give the smallest whole number ratio of the positive and negative particles that result in no electrical charge. So in this case, that would be 1 sodium and 1 chlorine ion. So when we look at matter now, we know that matter can be divided as into either mixtures or pure substances. So here is the pure substance branch. So we've got matter up here, which can be divided as being either a mixture or a pure substance. We're looking just at the pure substances. Pure substances can be described as being either elements or compounds. In elements, we have only one kind of atom present. Elements can be of 2 types. Most of the elements on the periodic table are individual atoms. A few elements on the periodic table exist as homoatomic molecules, and we pointed out those diatomic 7. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all exist as homoatomic molecules. The other kind of pure substance is a compound. And in compounds, we have 2 or more different kinds of atoms present. And compounds are of 2 types. There are those that are composed of heteroatomic molecules, And then there are those where there are no molecules, but rather there is an extended array of positive and negative particles called ions that go on and form a crystal. So, molecules are two or more atoms chemically bound together in a discrete unit. You can't divide molecules by physical means. Molecules can be classified in one of two ways, either by the number of atoms that are present, so diatomic, triatomic, and polyatomic molecules, and also on the basis of the types of atoms present. So if we have an element that's made of molecules, that would be composed of homoatomic molecules, and if we have a compound that is composed of molecules, then that compound would be composed of heteroatomic molecules. There are a few compounds that are made of charged particles that don't contain molecules. These are referred to as ionic compounds, and we'll talk more about those a little later on. This third section that I'm going to talk about is quite brief. It really follows on from Dalton's work, and it's a discussion of natural and synthetic compounds. The physical and chemical properties of a compound or an element are determined entirely by the number of atoms that it contains and how those atoms are connected to one another, that is, their arrangement. So, for example, sucrose is this disaccharide that looks like this. It has a bunch of carbon atoms, hydrogen atoms, and oxygen atoms. Sometimes we'll kind of see the suggestion of things being described as being natural or man-made, and that there'll be some distinction between a natural compound and the man-made compound. And this is completely incorrect, because the only thing that determines the physical and chemical properties of a substance are the arrangement and number of atoms that it contains. It is not in any way determined by whether it is man-made or natural. So the properties of a compound are determined by the number, type, and arrangement of the atoms they contain. Those properties are not determined by the origin of the compound and whether it is natural or synthetic.